way to solve these. 12.4 is the how you do these problems, and it actually works for things that are arrangements that are ridiculous and you can't do as a physics student. But the rules are the same. This is what you do. You write something as KQ over D squared. You take a look at it, try to figure out this geometry of one of them, and then you sum it up as you change from one spot to another spot. All right, Peter, you want the last one?
No. I'm done.
Thank you for volunteering.
Class.
All right. So,
I really don't.
I know
Want
someone
I
who's
never
a
remember arc length. So.
I go, what's the least
I
developed
would
country
actually
in
use
Europe?
let's see.
I never remember an arc length.
It's so rounded by a so
Yes, this counts just as much as health class. All right.
Okay, really.
There's many units.
I want to be in health class instead of
Yo, can I like destroy whoever designed this?
Okay. So I've got a semicircle or part of a semicircle. Any part will work. It has to be symmetrically arranged around my thing. The only place I find electric field is right there, so that's kind of a one dot spot. Most of these other ones, I could use it to generalize a approaching and moving away approach. This one, you cannot even do that with. This one is just one spot in space, but it's going to look an awful like your question of the week. So that's probably a good one for me to generalize for you to have. I'm going to, actually, you know what? Let's set some bounds on this so it doesn't actually look like 90 degrees. So I'm going to go ahead and make this. What angles do you want to make this?
60.
60, but of course, we're going to do calculus on this, so we're absolutely not going to use 60 degrees. We're going to use pi over 3 and pi over 3. Agreed? Negative pi over 3?
Yes.
Okay. How you doing, Peter?
Terrible.
Oh, come on. This is fun.
No, it's not.
This is not fun? You sure it's not fun?
Wait, pi over 3?
Pi over 3 and negative pi over 3.
Pi over 3.
60 degrees.
No. Like the top.
From the center up to that spot up there.
Okay.
This angle here. That's a good question. Everybody got that?
I can't.
Actually, they did it the other way around, didn't they? I should probably draw it the same way they did it. Whatever. We're wild.
Does it matter?
We're crazy. We're going to go a different way today. It's going to be all right. They also did 60 degrees, which is
60.
awful and not a good choice. Okay, so I look at this problem and I go, okay, what a electric field caused by this guy right here. I love it. What is that electric field going to be caused by a small infinitesimal piece? Electric field caused by one thing. Go, sir. KQ over D squared. And I'm going to use R. Is that okay with you?
Yeah.
In this case, it's very good because it's the radius of the circle, is it not? And then we start to think, hey, maybe we'll have to use calculus on this one because why?
Distance.
The distance is the same all the way through, so there's no way that's what's messing us up. We got an R. We're good. We don't have to use calculus. Hold on a second. We still have some other things to play with. So this one here causes a electric field this direction, agreed? And it's equal to KQ over R squared. But you see a problem. When this one creates a field, and it's, let's say it's the same angle down, what happens?
It offsets.
It offsets, which means I end up with KQ over R squared times what, sir?
0.
Okay, let's draw them out. I got this one, I got this one. What cancels out? You probably said it because he's even you. So these cancel out. So I got what?
Cosine.
Cosine theta. You said it 3 times. I just now catching up to you. Didn't say it right the first time. I was busy whining. I couldn't hear you. Okay, so good?
Yes.
Okay, now here's the problem. What does change? The theta is changing, which changes how big a force each one of these stupid little pieces gives us. So close. So we need to integrate with respect to theta, which means I need to describe my Q in terms of theta. So now we got to talk about how do we describe this. So let's talk about what we know about this. We know that as a charge field length, because it says so in the problem, even though we haven't read it yet. Even if it doesn't, I will make it so by saying total charge divided by the length of the piece of wire. Agreed? That's going to be equal to, we know that's going to equal to our distance x times, oh wait, I'm doing wrong here. Hold on. I'll do that backwards. It's going to be equal to our distance x is equal to q, right? Our charge field length times the length we're talking about. But I want to talk about that length in terms of a curve, which is a problem, And I want to talk about it in terms of theta, if I can at all possibly do so, so I can integrate properly.
Wait, isn't that R? R. S equals R theta.
S equals R theta. You guys came up with it. I don't know if every year does that, so that's good news. So the length there is R theta, is it not? And therefore, RQ would be equal to theta lambda, charge me a length, times the little tiny piece that I have on there. We're assuming theta is a small piece.
So is that a D theta?
We're going to turn it into a d theta, aren't we? Because why do we have to turn it into d theta? Because every little angle changes it, right? So we're going to have to change Q into a d theta. So here we go. Our electric field is therefore going to be summing up all the pieces of K. So Q is going to be lambda R. Since we have cosine theta and we have theta, we're going to have to take the integral. So replace the theta with a d theta over R squared.
No,
Where am I starting my integral?
These R's are the same though, aren't they?
These R's are the same, so they can be canceled out in a moment, which is a good thing. Oh, it's going to lead to a problem, though. I can see it already. Whoops. Okay, well, you guys learned something before the rest of the class does.
No, wait.
You were like 2 days away from it.
Fine.
Like literally after the test, we'll do like drawing some pictures for like 2 days, and then we'll do this one. It'll be the very next identity we learn.
Right.
So you might as well get, it's going to be on the next calculus test for certain. Okay, so cosine theta, where are we going to start our integral? Negative pi over 3. We're going to enter integral pi over 3. All right. Oh, no, I'm wrong. We don't have to learn anything new because we just had to do integral. These are all constants, right? So they got in front.
Yeah.
So K lambda over R, integral from negative pi over 3 to pi over 3 cosine theta d theta. And what's the integral of cosine? Sine theta.
Oops. Yeah.
Derivative of sine is cosine, right? No, I'm with you. I do that every time. I pause for a while, go wait. Yeah. No, that's right. We're loud. And then how do I solve for it? K lambda over R times sine of pi over 3 minus. Wait, this is negative, wasn't it? No, it's not negative. My bad. Minus K lambda sine negative pi over 3 all over R. And we'd be on our way. That's it.
What's that sign like?
It's K lambda sine negative pi over 3.
Oh, okay.
All right, my bad. I just put it in the bounds.
What is this not hard?
That's it. That's the nastiest part of the chapter. We're done with it.
Yeah, that was simple.
I'm not saying that. I believe I just said it's the nastiest part of the chapter. And we're all done with it. Look at that. Isn't that nice?
So are we gonna practice with some of these?
Yes.
Okay.
In fact, your first free response is one of these, right? Your first response to your first question of the week that you currently have is one of these.
Oh, it's the same.
It's
the same circle.
About where S
Hold on.
equals R over theta came from.
What's that?
The S equals R over theta.
R times theta?
Yeah.
That's the arc length, right? That is the length of a curve around a circle. If you know the radius R and you know the angle is theta, and you use radians.
Oh,
Okay?
Okay.
All right, because it equals R theta. That's what?
Arc length.
Arc length. It's arc length. All we say is how far is the arc length. So a little bitty piece, we modeled it as R theta, and then if we're talking about a really small piece, we can do R d theta as we integrate through the d thetas.
Oh.
That's what we did. Good? Happy? Sad? Ready to celebrate good times? All right, now some caveats. Some caveats to this thing. Caveat number 1. They only expect about 1 in 5 students to be able to do any of these 4.
So then we're gonna make it really.
So if you get to the test and you go, oh yeah, I should have studied that, don't stare at it for an hour and a half. It's not going to do you any good. If you don't got it, you don't got it. By the way, write this down. Electric field equals KQ over R squared. 50-50 chance that's one of the 3 points that's probably awarded for that.
Wait, hold on. Is it always pi over 3 or?
No, it's going to be whatever the bounds are. So I chose one that was pi over 3. If it was theta, it would just be theta and theta. I probably should have left it as theta 1 and theta 2.
Okay.
Kind of want to be more concrete because you guys were looking at me a little strange about the curve. But yeah, it should be theta 1 minus theta 2 or theta 2 minus theta. They have to be symmetric though because we're canceling out the up-down components, right? So where the bottom is, it's going to be the same top. Yes, sir.
Would we see something like where they give us the answer and they say show that this is the answer?
That's what I was about to say. Because they expect only 1 out of 5 students to do this problem, they're almost always going to give you the answer. Which means you know you have to write this down for 1 point. You know what the answer looks like. If you can just remember the trick, you can get the other 2 points. If you're trying to derive it from original principles, you better have a lot of time on your hands because it's going to take you a while. Oh, yeah, that's the trick. Don't want to be doing that. And be aware that since they gave you the answer, what do they expect you to do? Move on to the next pieces, right? They want you to go ahead and use electric field to find voltage or something. They want you to find the force at some distance away from it. They're going to make you answer all those questions, right? So they make you answer all those questions. Those are the questions where most of the points are. That's what you have to be able to do, and that's what you're going to do. But if I don't show this to you once, I'm pretty much setting you up for failure, right? Not only that, but if you actually plan on being an electrical engineer, this is the beginning of several very awful problems that are in your future. Because they'll put they won't ask what is the electric field here next to a line of charge. They won't ask it here. They're going to ask it there.
Are they gonna ask it?
That's when you're in your junior year class deciding to where's your add drop slip because that's not fun.
Can they do any worse of a spot than that?
Oh yeah.
What's
Oh, yeah.
the worst
Look,
spot?
look. This is how to make the problem worse. Here's my charge distribution, and I want to know the electric field here. So then you're gonna have to use linear algebra.
Oh, I thought he literally fell.
Yeah. You'd have to use linear algebra to unbend the wire.
Is that what linear algebra?
Do the math. Yes.
I didn't know that.
Then do the math. Then do the math, and then snap the wire back in and figure out what the answer actually is. To unbend it, you're going to have to use a matrix where each integral is going to be dependent on a different variable. Because it's set all up right. So, yes, they can do this to you. Now, I'm being unfair to electrical engineers, I'll be frank. Electrical engineers do this a couple of times and then they forget about it immediately because why do this? It hurts your head. It's only physicists that get stuck doing this for eternity.
What sick twisted individual came up with that problem?
Sorry, what?
What sick twisted individual came up with that type of problem?
I don't know. Probably somebody was trying to figure out what a wire like this would have for a charge.